All right, this is number 5, elephant toothpaste, which is kind of a fun experiment. Okay, so you can write down what happens in the video. All right, the chemical equation for that is basically this H2O2 is decomposing into water and oxygen gas, okay? So the question is, the volume of a small swimming pool is about 375,000 liters. How many moles of H2O2 would be needed to fill the pool with 75,000 liters of oxygen gas? Okay, so now this one's a little bit trickier, right? Because the density of oxygen gas is given, all right? But now we're seeing something in liters, which we have not seen before, okay? So the beauty of the BCA table is you can use it no matter what, as long as you first put it into moles, okay? So in this case, my given is going to be 375,000 liters of O2, okay? But I need to get to moles, right? So before I can get to moles, I need to get to grams. So I'm going to use this density of 1.43 grams in a liter, okay, right? And now I'm back where I usually am with grams. So O2, there's going to be, 32 grams of O2 in 1 mole of O2, right? I get this from the periodic table, 2 oxygens, okay? And then that's going to go away. And then I'm going to be left with moles of O2, okay? So you can use the BCA table in any way, as long as you first put it into moles by doing whatever kind of conversions you have to do to make that happen, okay? So 375,000 times 1.43 divided by 32. Whoops, oh shoot. 375,000 times 1.43 divided by 32. Holy moly, this is going to be a lot. 16,758 moles of oxygen. That is a lot. Okay. All right. So the oxygen, right, is what's going to be given. I mean, what we're going to make. Okay, so this is going to be down here. Remember, the products are going to start with nothing. So everything here is going to be based on that amount. All right. So this is going to be 16,758. That's an awful lot. Okay, and that's a plus. And this is going to be a minus. Okay, and then the ratios. Okay. All right, so before I do the ratios, I need to go up and balance, which I should have done first, but, you know, it's midnight and I'm tired. Okay, all right, so what I see here when I balance is I have O2 and then a single O, okay, which is going to be an odd number. And this over here on the left is O2, which is never going to be able to be odd. So the first thing I'm going to do is try a 2 here, because that makes the oxygens even at least, okay? So when I have 2 here, 2 H2s, now I have to put a 2 here, okay? That's going to give me now 4 oxygens on the left and 4 oxygens on the right, so I'm all set, okay? All right, so back to my BCA table. My given was 1, so that's going to go on the bottom, okay? And then the coefficient on the top, right? Because a 2 to 2 to 1 ratio means if this 1 is my given, everybody else is going to need double the amount, okay? So 16,758 times 2, that's an awful lot. 3,3,516, okay, to be left with nothing. Okay, and then this one is going to be also 3,3,516 moles of water. Okay. All right. Okay, type of reaction. I guess we'll call this one a decomposition. That's splitting apart into smaller parts. Okay, my word equation is going to be 33,516 moles of H2O2. You probably won't know this one, but if you see in the video, I think it's hydrogen peroxide, okay? Aqueous, because, you know, I always forget that, decomposes to form 3,3,516 moles of liquid water and 16,758 moles, of oxygen gas. All right. Okay, my final answer is supposed to be in grams or moles, so let's go back and see what we were looking for. We actually only wanted how many moles of H2O2, so hallelujah, we're already done. Okay, we don't even need to do this part. I can just look at the BCA table and see that it is 33,516 moles of H2O2.